Good evening, friends, and welcome to Sleepy Time Tales, a podcast aimed at helping you to get a good night's sleep. This is a podcast where I read all the books, sometimes fiction, sometimes non-fiction, in the most boring way I can, to try help slow your spinning mind, enough for you to fall asleep in the most natural way possible. The stresses of life often follow us to bed and keep us company, but I'm here to distract you from them and help you drift away. Before you do fall asleep, if you enjoy Sleepy Time Tales and it helps you to get a good night's sleep, and you would like to help me keep it going, please consider signing up on the Patreon at patreon.com/sleepytimetales. This is monthly support that starts at $2 a month. It goes a long way to help me cover costs and do what's necessary for the show. If monthly is a big ask, then you can throw a tip in the tip jar in the Ko-Fi, which is linked in the show notes. And if you want to support the show but don't have the means or don't want to support it financially, you can just tell people about it. If you know someone who's struggling to sleep, tell them where to find the show and leave it at that. Anyway, enough of that. Let's start learning what they believed in the 1920s about Mars and the possibility of life out there in our solar system. Snuggle down, close your eyes, breathe deeply and listen closely as I lead you down the path to sleep. We return today to Astronomy, the Science of the Heavenly Bodies, by David P. Todd. Chapter 32, The Ruddy Planet. Mars is a planet next in order beyond the Earth, and its distance from the Sun averages 141.5 million miles. It has a relatively rapid motion among the stars. Its color is reddish, and when nearest to us, it is perhaps the most conspicuous object in the sky. Mars appeared to the ancients just as it does to us today. Aristotle recorded an observation Mars 356 BC, when the moon passed over the planet, or occulted it, as our expression is. Galileo made the first observations of Mars with a telescope in 1610, and his little instrument was powerful enough to enable him to discover that the planet had phases, though it did not pass through all the phases that Mercury and Venus do. This was obvious from the fact that Mars is always at a greater distance from the Sun than we are, and the phase can only be gibbous, or about like the moon when midway between full and quarter. Many observers in the 17th century followed up the planet with such feeble optical power as the telescope of that epoch provided. Fontana, who made the first sketch, Riccioli and Bianchini in Italy, Cassini in France, Huygens in Holland, and later Sir William Herschel in England. It was Cassini who first made out the whitish spots or polar caps of Mars in 1666, but not until after Huygens had noticed the fact that Mars turned round on an axis in a period but little longer than the Earth's. Cassini followed it up later with a more accurate value, and observations in our day, when combined with these early ones, enable us to say that the Martian day is equal to 24 hours, 37 minutes, 22.67 seconds, accurate probably to the 100th part of a second. When we know that a planet turns around on an axis, we know it has a day. When we know the direction of the axis in space or in relation to the plane of its path around the Sun, we know that it has seasons. We can tell their length and when they begin and end. It did not take many years of observation to prove that the axis around which Mars turns is tilted to the plane of its path around the Sun by an angle practically the same as that which the Earth's axis is tilted. So there is the immediate inference that on Mars the order and perhaps the character of the seasons is much the same as here on the Earth. At least two things, however, tend to modify them. First, the year of Mars is not 365 days like ours, but 687 days. Each of the 4 seasons on Mars, therefore, is proportionally longer than our seasons are. Then comes the question of atmosphere. How much of an atmosphere does Mars really possess in proportion to ours, and how would its lesser amount modify the blending of the seasons into one another? All discussion of Mars and the problems of existence of life upon that planet hinge upon the character and extent of Martian atmosphere. The planet seems never to be covered, as the Earth usually is, with extensive areas of cloud, which an observer in space would completely mask its oceans and continents. Nearly all the time, Mars in his equatorial and temperate zones is quite clear of clouds. A few whitish spots are occasionally seen to change their form and position in both northern and southern latitudes, and they vary with the progress of the day on Mars, as clouds naturally would. But Schiaparelli, perhaps the best of all observers, thought them to be not low-lying clouds of the nimbus type that would produce rains, but rather a veil of fog, or perhaps a temporary condensation of vapor as dew or hoarfrost. But the strongest argument for an atmosphere is based on the temporary darkening or obscuration of well-known and permanent markings on the surface of Mars. These are more or less frequently observed, and clouds afford the best explanation of their occurrence. So much for evidence supplied by the telescope alone. When, however, we employ the spectroscope in conjunction with the telescope, another sort of evidence is at hand. Several astronomers have reached the conclusion that watery vapor exists in the atmosphere of Mars, while other astronomers equipped with equal or superior apparatus, and under equally favorable or even better conditions, have reached the remarkable conclusion that the spectra of Mars and the Moon are identical in every particular. From this we should be led to infer that Mars has perhaps no more atmosphere than the Moon has. That is to say, none whatever that present instruments and methods of investigation have enabled us to detect. What then shall we conclude? Simply that the atmosphere of Mars is neither very dense nor extensive. Perhaps its lower strata close to the planet's surface are about as dense as the Earth's atmosphere is at the summits of our highest mountains. This conclusion is not unwelcome, if we keep a few fundamental facts in clear and constant view. Mars is a planet of intermediate size between the Earth and the Moon, twice the Moon's diameter, 2,160 miles, very nearly equals the diameter of Mars, 4,200 miles, and twice the diameter of Mars does not greatly exceed the Earth's diameter, 7,920 miles. As to the weights or masses of these bodies, Mars is about 1/9 and the Moon 1/80th of the Earth. The atmospheric envelope of the Earth is abundant. The Moon has none as far as we can ascertain, so it seems safe to infer that Mars has an atmosphere of slight density, not dense enough to be detected by spectroscopic methods, but yet dense enough to enable us to explain the varying telescopic phenomena of the planet's disk, which we should not know how to account for if there were no atmosphere whatever. One astronomer has indeed gone so far as to calculate that in comparison with our planet, Mars is entitled to 1/20th as much atmosphere as we have, and that the mercurial barometer at sea level would run about 5.5 inches, as against 30 inches on the Earth. In general, then, the climate of Mars is probably very much like that of a clear season on a very high terrestrial tableland or mountain. A climate of wide extremes with great changes of temperature from day to night. The inequality of Martian seasons is such that in his northern hemisphere, the winter lasts 381 days, and the summer only 306 days. Now the polar caps of Mars, which are reasonably assumed to be due to snow or hoarfrost, attain their maximum 3 or 4 months after the winter solstice, and the minimum about the same length of time after the summer solstice. This lagging should be interpreted as an argument for a Martian atmosphere with heat-storing qualities, similar to that possessed by the Earth. Upon this characteristic, indeed, depends the climate at the surface of Mars, whether it is at all similar to our own, and whether fluid water is a possibility on Mars or not. While the cosmic relations of the planet and its orbit are quite the same as ours, nevertheless the greater distance of Mars diminishes his supply of direct solar heat to about half of what we receive. On the other hand, his distance from the Sun during his year of motion around it varies much more widely than ours, so that he receives when nearest the sun about 1/2 more of solar heat than he does when furthest away. Southern summers on Mars, therefore, must be much hotter, and southern winters colder than the corresponding seasons of his northern hemisphere. Indeed, the length of southern summer nearly twice that of the terrestrial season sometimes amply suffices to melt all the polar ice and snow, as in October 1894, when the southern polar cap of Mars dwindled rapidly and finally vanished completely. Very interesting in this connection are the researches of Stoney on the general conditions affecting planetary atmospheres and their composition. According to the kinetic theory, if the molecules of gases which are continually in motion travel outward from the center of a planet, as they frequently must, and with velocities surpassing the limit that a planet's gravity is capable of controlling, these molecules will effect a permanent escape from the planet and travel through space in orbits of their own. So the moon is wholly without atmosphere because the moon's gravity is not powerful enough to retain the molecules of its component gases. So also the Earth's atmosphere retains no helium or free hydrogen. So too Mars is possessed of insufficient force of gravity to retain water vapor, and the Martian atmosphere may therefore consist mainly of nitrogen, argon, and carbon dioxide. As everyone knows, the axis of the Earth, if extended to the northern heavens, would pass very near the North Polar Star, which on that account is known as Polaris. In a similar manner, the axis of Mars pierces the northern heavens about midway between the two bright stars, Alpha Cephei and Alpha Cygni, Deneb. The direction of this axis is pretty accurately known, because the measurement of the polar caps of the planet as they turn around from night to night, year in and year out, has enabled astronomers to assign the inclination of the axis with great precision. These caps are brilliant white, and they are generally supposed to be snow and ice. The wax and wane alternately with the seasons on Mars, being largest at the end of the Martian winter and the smallest near the end of summer. The existence of the polar caps, together with their seasonal fluctuations, afford a most convincing argument for the reality of a Martian atmosphere, sufficiently dense to be capable of diffusing and transporting vapor. The northern cap is centered on the pole almost with geometric exactness, and as far as the 85th parallel of latitude. On the other hand, the solar polar cap is centered around 200 miles from the true pole, and this distance has been observed to vary from one season to another. No suggestion has been made to account for this singular variation. On one occasion it stretched down to Martian latitude 70 degrees and was over 1,200 miles in diameter. Pickering watched the changing conditions of the shrinking of the South Polar Cap in 1892 with a large telescope located in the Andes of Peru. Mars was faithfully followed on every night but one from July 13th to September 9th, and the apparent alterations in this cap were very marked, even from night to night. As the snows began to decrease, a long dark line made its appearance near the middle of the cap, and gradually grew until it cut the cap in two. This white polar area, and probably also the northern one in similar fashion, becomes notched on the edge with the progress of its summer season. Dark interior spots and fissures form, isolated patches separate from the principal mass, and later seem to dissolve and disappear. Possibly, if one were located on Mars and viewing our Earth with a big telescope, the seasonal variation of our north and south polar caps might present somewhat similar phenomena. All the recent oppositions of Mars have been critically observed by Pickering from an excellent station in Jamaica. Quite obviously, the fluctuations of the polar caps are the key to the physiographic situation on Mars, and they're made the subject of the closest scrutiny at every recurring opposition of the planet. Several observers, Lowell in particular, record a bluish line or a sort of retreating polar sea following up the diminishing polar cap as it shrinks with the advance of summer. It is said that no such line is visible during the formation of the polar cap with the approach of winter. All such results of critical observation, just on the limit of visibility, have to be repeated over and over again before they become part of the body of accepted scientific fact. And in many instances, the only sure way is to fall back on the photographic record, which all astronomers, whether prejudiced or not, may have the opportunity to examine and draw their individual conclusions. Already the approaching opposition of 1924, the most favorable since the invention of the telescope, is beginning to attract attention, and preparations are in progress of new and more powerful instruments, with new and more sensitive photographic processes, by means of which many of the present riddles of Mars may be solved. Chapter 33. The Canals of Mars. Then there are the so-called canals of Mars, about which so much is written and relatively little known. Faint markings which resemble them in character were first drawn in 1840 and later in 1864. But Schiaparelli, the famous Italian astronomer, is probably their original discoverer, when Mars was at its least distance from the Earth in 1877. He made the first detailed map of Mars at this time, and most of the important, or more conspicuous canals, canali he called them in Italian, that is channels merely, without any reference whatever to there being watercourses, were accurately charted by him. At the subsequent close approaches of Mars, the canals have been critically studied by a wide range of astronomical observers, and their conclusions as to the nature and visibility of the canals has been equally wide and varied. The most favorable oppositions have occurred in 1892 and 1894, also in 1907 and 1909. On these occasions, a close minimum distance of Mars was reached, that is about 35 millions of miles. But in 1924, the planet makes the closest approach in a period of nearly 1,000 years. This distance will not much exceed 34 millions of miles. But although this is a minimum distance for Mars, it must not be forgotten that it is a really vast distance, absolutely speaking. It is something like 150 times greater than the distance of the Moon. With no telescopic power at our command, could we possibly see anything on the Moon of the size of the largest buildings or other works of human intelligence, so that we seem forever barred from detecting anything of the sort on Mars? Nevertheless, the closest scrutiny of the ruddy planet by observers of great enthusiasm and intelligence, coupled with imagination and persistence, have built up a system of canals on Mars, covering the surface of the planet like spider webs over a printed page, crossing at each other at intersecting spots known as lakes, and embodying a wealth of detail which challenges criticism and explanation. To see the canals at all requires a favorable presentation of Mars, a steady atmosphere and a perfect telescope, with a trained eye behind it. Not even then are they sure to be visible. The training of the eye has no doubt much to do with it. So photography has been called in, and very excellent pictures of Mars have already been taken, some nearly half as large as a dime, showing plainly the lights and shades of the grander divisions of the Martian surface, but only in a few instances revealing the actual canals more unmistakably than they are seen at the eyepiece. The appearance and degree of visibility of the canals are variable. Possibly clouds temporarily obscure them, but there is a certain capriciousness about their visibility that is little understood. In consequence of the changing physical aspects, as to season on Mars and his orbital position with reference to the Earth, some of the canals remain for a long time invisible, adding to the intricacy of the puzzle. For the most part, the canals are straight in their course and do not swerve much from a great circle on the planet, but their lengths are very different, some as short as 250 miles, some as long as 4,000 miles, and they often join one another like spokes in the hub of a wheel, though at various angles. As depicted by Lowell and his corps of observers at Flagstaff, Arizona, the canal system is a truly marvelous network of fine darkish stripes. Their color is represented as a bluish green. Each marking maintains its own breadth throughout its entire length, but the breadth of all the canals is by no means the same. The narrowest are perhaps 15 to 20 miles wide, and the broadest probably 10 times that. At least that must be the breadth of the Nilocertus, which is generally regarded as the most conspicuous of all the canals. The Lowell Observatory has outstripped all others in the number of canals seen and charted, now about 500. What may be the true significance of this remarkable system of markings, it is impossible to conclude at present. Schiaparelli, from his long and critical study of them, the changes of width and color, was led to think that there may be a variable hydrographic system for distributing the liquid from the melting polar snows. In this case, it would be difficult to escape the conviction that the canals have, at least in part, been designed and executed with a definite end in view. Lowell went even further and built upon their behavior an elaborate theory of life on the planet, with intelligent beings constructing and opening new canals on Mars at the present epoch. Pickering propounded the theory that the canals are not water-bearing channels at all, but that they are due to vegetation, starting in the spring when first seen and vitalized by the progress of the season poleward, the intensity of color of the vegetation coinciding with the progress of the season as we observe it. Extensive irrigation schemes for conducting agricultural operations on a large scale seem a very plausible explanation of the canals, especially if we regard Mars as a world farther advanced in its life history than our own. Erosion may have worn the continents down to their minimum elevation, rendering artificial waterways not difficult to build, while with the vanishing Martian atmosphere and absence of rains, the necessity of water for the support of animal and vegetal life could only be met by conducting it in artificial channels from one region of the planet to another. Interesting as this speculative interpretation is, however, we cannot pass by the fact that many competent astronomers with excellent instruments finely located have been unable to see the canals, and therefore think the astronomers who do see them are deceived in some way. Also, many other astronomers, perhaps on insufficient grounds, deny their existence in toto. Many patient years of labor would be required to consult all the literature of investigation of the planet Mars, but much of the detail has been critically embodied in maps at different epochs, by Kaiser, Proctor, Green, and Dreyer, and Flammarion in 2 classic volumes on Mars has presented all the observations from the earliest time, together with his own interpretation of them. Areography is a term sometimes applied to a description of the surface of Mars, and it is scarcely an exaggeration to say that areography is now better known than the geography of immense tracts of the Earth. For some reason well recognized, though not at all well understood, Mars, although the nearest of all the planets, Venus alone excepted, is an object by no means easy to observe with the telescope. Possibly its unusual tint has something to do with this. With an ordinary opera glass, examine the moon very closely and try to settle precise markings, colors, and the nature of objects on her surface. Mars, under the best conditions, scrutinized with our largest and best telescope, presents a problem of about the same order of difficulty. There are delicate and changing local colors that add much uncertainty. Nevertheless, the planet's leading features are well made out, and their stability since the time of the earliest observers leaves no room to doubt their reality as parts of a permanent planetary crust. The border of the Martian disk is brighter than the interior, but this brightness is far from uniform. Variations in the color of the markings often depend on the planet's turning round on its axis, and the relation of the surface to our angle of vision. If we keep in mind these obstacles to perfect vision in our own day, it is easy to see why the early users of very imperfect telescopes failed to see very much, and were misled by much that they thought they saw. Then, too, they had to contend, as we do, with unsteadiness of atmosphere, which is least troublesome near the zenith. As their telescopes were all located in the northern hemisphere of Mars is one of the best circumstanced for their investigation. because at the remote oppositions of Mars, which always happen in our northern winter with the planet in high north declination, it is always the north pole of Mars which is presented to our view, whereas the close off positions of the planets always come in our northern midsummer, with Mars in south declination, and therefore passing through the zenith of places in corresponding south latitude. With Mars near opposition, high up from the horizon, a fairly steady atmosphere, and a magnifying power of at least 200 diameters, even the most casual observer could not fail to notice the striking difference in brightness of the two hemispheres, the north chiefly bright and the south markedly dark. Formerly, this was thought to indicate that the southern hemisphere of Mars was chiefly water and the northern land, much as is the case on the Earth, with this difference, however, that water and land on the Earth are proportioned about as 11:4. But Mars in its general topography presents no analogy with the present relation of land and water on the Earth. There seems no reason to doubt that the northern regions, with their prevailing orange tint, in some places a dark red and in others fading to yellow and white, are really continental in character. Other vast regions of the Martian surface are possibly marshy, the varying depth of water causing the diversity of color. If we could ever catch a reflection of sunlight from any part of the surface of Mars, we might conclude that deep water exists on the planet. But the further research progresses, the more complete becomes the evidence that permanent water areas on Mars, if they exist at all, are extremely limited. Since 1877, Mars has been known to possess 2 satellites, which were discovered in August of that year by Hall at Washington. Moons of this planet had long been suspected to exist, and on 1 or 2 previous occasions critically looked for, though without success. In the writings of Dean Swift, there is a fanciful allusion to the 2 moons of Mars, and if astronomers had chanced to give serious attention to this, Phobos and Deimos, as Hall named them, might have been discovered long before. They are very small bodies, not only faint in the telescope, but actually only 10 or 20 miles in diameter. And from the strange relation that Phobos, the inner moon, moves around Mars 3 times, while the planet itself is turning around only once on its axis, some astronomers incline to the hypothesis that this moon, at least, was never part of Mars itself, but that it was originally an inner or very eccentric member of the asteroid group, which ventured within the sphere of gravitation of Mars, was captured by that planet, and has ever since been tributary it as a secondary body or satellite. Chapter 34. Life in Other Worlds. Popular interest in astronomy is exceedingly wide, but it is very largely confined to the idea of resemblances and differences between our Earth and the bodies of the sky. The question most frequently asked the astronomer is, have any of the stars got people on them? Or more specifically, is Mars inhabited? The average questioner will not readily be turned off with yes or no for an answer. He may or may not know that it is quite impossible for astronomers to ascertain anything definite in this matter, most interesting as it is. What he wants to find out is the view of the individual astronomer on this absorbing and ever-recurring inquiry. We ought first to understand what is meant by the manifestation here on the earth called life, and agree concerning the conditions that render it possible. Apparently they are very simple. We may or may not agree that a counterpart of life, or life of a wholly different type from ours, may exist on other planets under conditions wholly diverse from those recognized as essential to its existence here. The problem of the origin of life is, in the present state of knowledge, highly speculative and hardly within the domain of science. Here on Earth, life is intimately connected with certain chemical compounds, in which carbon is the common element without which life would not exist. Also hydrogen, oxygen, and nitrogen are present, with iron, sulfur, phosphorus, magnesium, and a few less important elements besides. But carbon is the only substance absolutely essential, Protoplasm cannot be built without it, and protoplasm makes up most of the living cell. Closely related to carbon is silica also, as a substitution in certain organic compounds. Protoplasm is able to stand very low temperatures, but its properties as a living cell cease when the temperature reaches 150 Fahrenheit. Animal life as it exists on Earth today appears to have been here many million years. The paleontologists agree that all life originated in the waters of the Earth. It has passed through evolutionary stages from the lowest to the highest. Throughout this vast period, the astronomer is able to say that the conditions of the Earth, which appear to be essential to the maintenance of life, have been pretty constantly what they are today. The higher the type of life, the narrower the range of conditions under which it thrives. Man can exist at the frigid poles, even if the temperature is 75 degrees below Fahrenheit 0. And in the deserts and the tropics, he swelters under the temperature of 115 degrees, but he still lives. At these extremes, however, he can scarcely be said to thrive. We have then a relatively narrow range of temperatures, which seem to be essential to his comfortable existence and development. We may call it 150 degrees in extent. Had not the surface temperature of the Earth been maintained within this range for indefinite ages, in the regions where the human race has developed, quite certainly man would not be here. How this equitability of temperature has been maintained does not now matter. Clearly the Earth must have existed through indefinite ages in the process of cooling down from temperatures of at least 6,000 degrees. During this stage, the temperature of the surface was Earth-controlled. Then this period merged very gradually into the stage where life became possible, and the temperature of this surface became, as it is now, Sun-controlled. How many years are embraced in the span of periods or ages we have no means of knowing, but of the sequence of periods and the secular diminution of temperature we may be certain. Then there is the equally important consideration of water necessary for the origination, support, and development of life. We cannot conceive of life existing without it. On the Earth, water is superabundant, and has been for indefinite ages in the past. There is little evidence that the oceans are drying up, although the commonly accepted view is that the waters of the Earth will very gradually disappear. Water can exist in the fluid state, which is essential to life, at all temperatures between 32 degrees and 680 degrees Fahrenheit. Air to breathe is essential to life also. The atmosphere which envelops the Earth is at least 100 miles in depth, and its own weight compresses it to a tension of nearly 15 pounds to the square inch at sea level. This atmosphere and its physical properties have had everything to do with the development of animal life on the planet. Without it and its remarkable property of selective absorption, which imprisons and diffuses the solar heat, it is inconceivable that the necessary equitability of surface temperature could be maintained. This appears to be quite independent of the chemical constituents of the atmosphere, and is perhaps the most important single consideration affecting the existence of life on our planet. If the surface of a planet is partly covered with water, it will possess also an atmosphere containing aqueous vapor. Heat, water, and air. These three essentials determine whether there is life on a planet or not. Of course, there must be nutrition suitable to the organism, mineral for the vegetal and vegetal for the animal. But the narrow range of variation appears to be the striking thing. Relatively but a few degrees of temperature and a narrow margin of atmospheric pressure. If this pressure is doubled or trebled, as in submarine caissons, life becomes insupportable. If, on the other hand, it is reduced even 1/3, as on mountains even 13,000 feet high, the human mechanism fails to function, partly from lack of oxygen necessary in vitalizing the blood, but mainly because of simple reduction of mechanical pressure. If then we conceive of life in other worlds, and it is agreed that life there must manifest itself much as it does here, Our answer to the question of habitability of the planets must follow upon an investigation of what we know, or can reasonably surmise about the surface temperatures of these bodies, whether they have water, and what are the probable physical characteristics of their atmospheres. And before we get to covering all the planets of the solar system, I'm going to call it there. As always, if you want to pick up where we're leaving off, you can find the original on Project Gutenberg at the link in the show notes. Thanks again for joining me on this episode of Sleepy Time Tales, the podcast designed around a bedtime story to help you to get a restful night. New episodes will be released every Sunday night to give you something fresh to help you rest in a new week. But make sure to follow or subscribe in whatever service you use so that you get your new episodes whenever they come out. Good night, and sweet dreams.